In this video, I will explain you the concept nuclear force. So last video we have learned about binding energy per nucleon, right? And we have seen certain trends with the graph. One is till mass number 30, we have seen that binding energy per nucleon is increasing, or I can say that below 30 the value of binding energy per nucleon is less, and above 170 it was again less. So in between this we have highest binding energy per nucleon, and that represent highest nuclear stability. So this binding energy per nucleon or binding energy, okay, this is per nucleon, right? So binding energy, I can call it as nuclear energy because that is the total energy available inside nucleus. Okay, so binding energy gives us the reason why this energy is present inside nucleus, due to binding of constituents of nucleus. That is the reason of binding energy, and that can also be termed as nuclear energy because this much energy is available inside nucleus, and on the reversing the process, that is splitting the nucleus into nucleon, we can expect release of so much energy. Okay, now see, binding energy per nucleon is due to, or binding energy is due to mass defect, right? So we have protons and neutrons, proton, neutron. I am taking the example of helium in this way. So they are going to get combined to form a nucleus. So after combination, we will have 2 proton inside nucleus and 2 neutron inside nucleus. But will this happen? Will this process happen spontaneously? See, we have 2 proton here, which will have repulsive force. What is the reason for this repulsive force? Coulomb's force in between 2 charges. That is equal to 1 by 4 pi epsilon 0 q1 q2 divided by r square. So here it will be plus E and plus E. R, see, for the combination we are bringing protons together. So when towards each other, so proton, whenever they are coming towards each other, the distance is getting decreased. Now it is R. Next moment R1, which is less than initial distance. Now again less, and here it will become a very small length. Okay, so under such small length, R will be very small and R square will be again small, and the whole Coulomb's law of repulsion would be very high. Okay, so on spontaneous combination is not possible because in between proton and proton we have strongest repulsive force when the distance in between them is small. Now when they are kept at a larger distance, force is less. But for nucleus, size of the nucleus is approximately 10 power minus 15, or measured in 10 power minus 12 to 10 power minus 15 meters. So at such a smaller length, the force would be very high. So to bind it together, we need a force which has got higher in magnitude as compared to Coulomb's law of attraction. Let's say Coulomb's law of repulsion in this case. If it is 100 Newton, then to overcome this, we need a force approximately 120 Newton or any value which is higher than Coulomb's law of repulsive force. Then only we can bind 2 protons together. See, just take an example of a magnet, a north side and north side. We have repulsive force, but I am applying a force which is larger than the repulsive force. So I can bring 2 north pole together, and maybe I can bring it so close to each other. The moment I withdraw my force, that will go apart, right? See, now which force is present inside 2 proton, and that will, there would be a force in between proton and neutron and neutron and neutron. So anyway, this is the explanation. To overcome the Coulomb's force of repulsion, we need a force which has got larger magnitude. Okay, now assume that these z number of proton and a minus z number of neutrons have been combined to form nucleus, and this nucleus is now having binding energy, and this binding energy is due to a strongest force present inside nucleus, and this is called as nuclear force. Hope the concept is very clear. Only a force can hold two protons together, okay, because there is Coulomb's law of repulsion. To oppose that force, we need a force which has got larger magnitude, then only it can be combined together to form a nucleus. Now this is the curve of nuclear force. See, what is the meaning of a negative potential energy? What is the energy? Just take an example, 1 by 4 pi epsilon 0 Q1 Q2 divided by R. This is the equation we have learned for potential energy. Now if one is positive and another charge is negative, then we know that it is attractive force. But what will happen to the potential energy? Positive and negative, the potential energy will become negative. But under such condition, the force is attractive. For example, one positive and one negative. On multiplication, this will become negative, and the whole potential energy will become negative. And negative potential energy says that the force is attractive, because positive charge and negative charge would be attracted each other. So this is just a concept. Just memorize that, or just remember conceptually that when the potential energy is negative, then the force is attractive in nature. When it is positive, the force is repulsive in nature. Okay. See the graph. This is the distance in between nucleon. Okay. Now, from here till here, see a fact that the potential energy, this is zero potential energy, okay, is negative for all value of distance in between nucleons from this value till 0.8 Fermi. You know the conversion of Fermi, right? Femtometer, 10 power minus 15 it is. Okay. 10 power minus 15 meters. Now see, here in between these two values, the force of attraction in between nucleon is very large, in such a way that it will become, the value will increase from here, from this point till 0.8 Fermi. This is 1 Fermi. So actually the highest nuclear force is not at 1 Fermi. It is slightly before 1 Fermi, which is 0.8 meter. Now see, this is 0.8 meter, say for example, okay, 0.8 Fermi. Now I am increasing the distance. What will happen? See, on increasing from 0.8 Fermi, we will reach 1 Fermi, where the nuclear force is less. Now after 1 Fermi, see, on reaching 2 Fermi, the force of attraction is decreasing, and approximately at 3 Fermi, or in between 2 and 3, the value becomes 0. What does it mean? See, nuclear force will come to existence only when the distance in between them is very small, less than 3 Fermi, I could say, or less than 2 Fermi. Okay, when we are increasing the distance in between them, at 3 Fermi, the force will become 0. So when I am taking two protons here, what is the distance in between them? Approximately 1, 2, 3, 4, 5, 6, yeah, 7 centimeter. 7 centimeter is larger than 3 or 2 Fermi. So let's say at 3 Fermi the force becomes 0. So this is obviously larger than 3 Fermi. 3 Fermi is 10 power 3 into 10 power minus 15 meters. Okay, so this is 7 centimeter is 7 into 10 power minus 2 meters. See, such a large value this one is. So when the distance is higher, there is no nuclear force. So nuclear force is a short-ranged force. See, immediately, even at a very smaller distance, the value of nuclear force becomes 0. So only when protons come together. So here only electrostatic force, Coulomb's law, Coulomb's force of repulsion. Here Coulomb's law, because this distance is not even comparable with 3 Fermi. So they are coming closer to each other only when the value in between them is so small that we can't visually inspect it. Such a small value that it comes less than 2 Fermi, there comes the existence of nuclear force, and nuclear force is maximum at 0.8 Fermi. Okay, so 2 point is, let's say this is 0.8 Fermi, nuclear force would be very high, but the moment you are making it 1 Fermi, it would be comparatively lesser, and the moment we are making it 3 Fermi, then the force is 0. So what are the properties of nuclear force here? One more thing I would say, that this nuclear force would be same in between proton and proton, and in between proton and neutron, and also in between neutron and neutron. So first property, nuclear force is the strongest force in the nature. First property. Second property, the nuclear force in between proton and proton, proton and neutron, and neutron and neutron is the same thing. Okay. See, now do we have an equation for finding the nuclear force? No, because we can't do experiment at a small length. See, nuclear force will only be present when the distance is less than 3 Fermi, and less than 3 Fermi is not practically inspected. We can't do an experiment at such a small distance. Okay, we can clearly do an experiment with nuclear force of attraction, gravitational force of attraction, and also with Coulomb's law of force of attraction. How can I do an experiment with Coulomb's force of attraction? Just charge a body, charge another body, and measure the force in between them. Change it to a different value, measure the force. Change this to a different value, measure the force. Change the distance, measure the force. And also with the gravitational force, 2 masses, measure the force. Make one mass heavier, measure the force. Make another heavier, measure the force. Separate them, measure the force. These measurements are possible, but here these measurements are not possible because we have to bring down the experiment to 3 femtometers, okay, or Fermi. So we don't have any equation, mathematical equation that represent the nuclear, that gives the mathematical value of nuclear force, but we have a graph of variation. So from this point till here it is increasing, then it is decreasing and reaching the point 0. So this says that nuclear force is only present in a short range, in a short distance in between them. So this says that nuclear force is a short ranged force, a very important quantity. Now, taking nuclear force into consideration, I will explain you the reason for variation of binding energy. Okay. Now, binding energy per nucleon is lesser for this nucleus having lesser mass number. Okay, lesser mass number means lesser number of nucleons. So in the case of H2, 2 nucleon, 3 nucleon, 4 nucleon, 6 nucleon. So the value, so initially the value is increasing. So 2 nucleon. So this is attracted by, in the case of H2, we have 1 proton and 1 neutron. So there is a nuclear force in between 1 proton and 1 neutron, and yeah, they are attracted. So I can say that only this is the attractive force. This would attract this and this would also attract this. Nuclear force is present. Now H3 means 1 proton and 2 neutrons. So what will happen? This proton would be attracted by neutron and also this neutron. So now with one person, 2 other persons are exerting force. So it would be more amount of nuclear force. Okay, so stability would be more in this case. To separate this proton, I have to give more amount of force as compared to this. Now in the case of He4 means 2 protons and 2 neutrons. So what will happen on this proton would be exerting a force, this neutron would be exerting a force, and even this neutron would be exerting a force. We need higher energy to break one proton from here. In the case of C12 means 6 proton and 6 neutron. So see, all the protons are exerting a force and all the neutrons are exerting a force. So on individual particle it would be present. So this is a higher force. See, nuclear, I could see nuclear force in between 2 nucleon is the same, but I can say that here this would experience higher force, this would be experiencing more higher force, highest, then keeping on going the value of nuclear force per nucleon will increase, and that is the reason for higher binding energy per nucleon till here. Now you may ask one more question, sir, after this also it should happen the same, right? Uranium-238 means we have 238 nucleons, right? So see, if I am just marking all the nucleons here, one would be exerted by nuclear force by all other nucleons, so it should be very difficult to break, right? But uranium-238 can be easily broken, and that has got radioactivity, or that has got a very less nuclear energy. And what is the reason for it? The reason is very simple. I told you, when the distance between two nucleons are increased, what will happen? This nuclear energy or nuclear force will decrease. Now I will take an example of an atom with, say for example, 36 nucleons. Okay. So as per this explanation, this would be exerted by an attractive force by all other nucleons. Every nucleon will be exerting an attractive force on this nucleus, and this should be more stable. But what will happen? See, this would be attracting this nucleus towards it. So these, not nucleus, nucleon. So these nearby protons and nearby neutrons would be exerting higher attractive forces. But see, now when I am comparing these nucleons are at a larger distance, right, away from this particular nucleon. I am only going to consider the total force on this nucleon. It can be a proton, it can be a neutron. So on this proton and neutron, all other nearby protons and neutrons are exerting force, but when we are going away from it, these are exerting force, but see, the distance in between them has got increased. This would be experiencing the highest force, but now we are increasing the distance in between nucleons on the arrangement. So what will happen? The force exerted by these many nucleons would be less compared to these forces. We are not done. See, on increasing the value, at some point the force even will become 0. Now again, if we are having one more layer of nucleons, what will happen? See, there are, beyond this point, these nucleons would not be able to give any amount of force on this nucleon. But nuclear force, in that case I could say that nuclear force is 0, but there will be Coulomb's law of repulsive force. See, after this point, after this I will mark it red. See, after this point, nuclear force is 0. See, 0. From here, it is the highest with nearby on increasing the distance, the force will decrease and become 0. Let's say with this layer. Now above that, the force, nuclear force in between the nucleons would be 0 or very less. But there would be repulsive force offered by Coulomb's law of force, or Coulomb's electrostatic force. Okay, so as we are moving away from one nucleon, we have seen that nuclear force is decreasing, and at the same time, when it compared with this electrostatic force given by Coulomb, that would be more significant at that location. So with this I could say that nuclear force is there, it is present and it is attractive in nature, but this will become significant. What is that? Electrostatic force of repulsion. And why it is repulsion? One proton and another proton, one proton and another proton, one proton and another proton. So when the distance increases, nuclear force decreases, and at the same time this electrostatic force of repulsion will become more significant, and thereby nucleus will become less stable. Okay, now this nucleus will have a tendency to break and to become 2 nucleus. So that is the reason for instability. Is that clear? See, higher the number of nucleons or higher the mass number, what will happen? The nuclear force in between nucleons decreases and force of repulsion due to Coulomb's law will become significant and thereby stability decreases. Here in this case, force increases because it is still in this range, in the short range. So force increases, higher nuclear force in between nucleons. So here it increases till this point, and after that, after certain point, this decreases due to the fact that the distance in between nucleons increases. This is a very important concept. Why binding energy per nucleon increases after 170 and it increases till 30. Okay, this may be asked in your board examination. Okay, thank you.